Hi, this is Mrs. LaBarbara. This is AP Physics Universal Gravitation Review number 5. An explorer plans a mission to place a satellite into a circular orbit around the planet Jupiter, which has mass mj equals to 1.9 times 10 to the 27 kilograms and a radius rj equals to 7.14 times 10 to the 7 meters. A. If the radius of planned orbit is r, use Newton's laws to show each of the following. Number 1. The orbital speed of the planned satellite is given by this equation. V equals to square root of g mj over r. Let's see. First, let's use Newton's laws. What does Newton's laws say? F net equals to ma. F net equals to ma. In this case, what is the F net? F net is Fg. So Fg equals to mac. What is Fg? Fg is g, the mass of explorer times the mass of Jupiter over r squared. This r is between the center of the explorer to the center of the satellite. That equals m times ac, which is v squared over r. From here, we solve for v. As you can see from this equation, the mass of the explorer doesn't really matter. So what is determined? What determines V is really the mass of the Jupiter and how far you are away from the Jupiter. So from here, we can solve for V equals to square root of g mj over r is exactly like what you're asked to do. Question 2 of part A. You need to prove period of the orbit is given by this expression t equals to square root of 4 pi squared r cubed divided by g times mj. So from kinematics, we know v, this is constant speed. Constant speed v equals d over t. But since the explorer is in a circle, in one period, it's the distance traveled by the explorer is the circumference 2 pi r. From here, we can solve for t. We already know v from part 1. So simply substituting that v in, you will get t equals to square root of 4 pi squared r cubed divided by g times mj. So here is again 2 pi r over v. When you divide a fraction, you multiply its reciprocal. So this becomes 2 pi r times square root of r divided by g times mj. This r is square root of r squared. So square root of r squared times r give you square root of r cubed. And 2 pi equals to square root of 4 pi squared. And that's how it came about. Question B. The explorer wants the satellite's orbit to be synchronized with Jupiter's rotation. This requires an equatorial orbit whose period equals to Jupiter's rotation period of 9 hours and 51 minutes, which equals to 3.55 times 10 to the 4 seconds. You need to determine the required orbital radius in meters. Remember, this radius is different from rj. It has to be above the surface of Jupiter. So from last question, we already know t equals to square root of 4 pi squared times r cubed divided by g mj. From here, we already know what t is. We know what mj is. You need to solve for r cubed. So just to refresh from your algebra, how do we go about it? First, you need to square both sides. Then you solve for r cubed. Lastly, you solve for r. So r equals to t squared times g times mj divided by 4 pi squared, and the whole thing to the power of 1/3. Simply substitute the numbers in your calculator. Remember, when you divide, you need to put a parentheses of 4 pi squared again, okay? You should get r equals 1.59 times 10 to the 8 meters. Question C. Suppose that injection of the satellite into orbit is less than perfect for an injection velocity that differs from the desired value in each of the following ways. Sketch the resulting orbit on this figure. J is the center of Jupiter, the dashed circle is desired orbit, and P is injecting point. Also describe the resulting orbit qualitatively but specifically. A, when the satellite is at a desired altitude, right, at point P, its velocity vector has the correct direction. Suppose it's going to the left in this case, but the speed is slightly faster than the correct speed for the circular orbit. What would the new orbit be? The new orbit will become elliptical, with J as one of its foci. So because the speed is faster, your new orbit would be bigger than the circle. So it's elliptical with J as one of the foci. So you have to, again, to describe the resulting orbit using words. Part 2 is when the satellite is at a desired altitude over the equator, its velocity vector has the correct direction, but this time the speed is slower than the correct speed of the circular orbit. Again, if the speed is less, then it's not a circle, it becomes elliptical. But in this case, it would be a smaller elliptical, again with J as one of its foci. Again, you need to describe the shape of the orbit, which is an ellipse, with point J as one of the foci. That's it for today. Thanks for watching. See you next time.